Please confirm that you can see the presentation. Hello, I ask you to confirm.
Yes, sir, we can see.
Thank you. So let us begin now. If you recall what we discussed a week ago, last Wednesday, because Friday we did not have classes, we were discussing the solution of Laplace's equation depending on only one variable in all the three coordinate systems. So earlier we had talked about solving Laplace's equation in the Cartesian coordinate system x, y, z. So if you were solving for Laplace's equation as it depended only on one variable, then whatever you do for any one coordinate will also apply to the other two coordinates. We worked for z, but we discussed that the similar solutions could also be found along the x and y coordinates. Okay, then we talked about, certain general properties. I intend to send you some extra notes based on these general properties. Then we talked about cylindrical coordinates, S, Y, Z system. And in each one of them, we solved, for each one of these coordinates, we solved Laplace's equation. And what we found was that for the Z coordinate, as in this direction, and the phi coordinate, as in this direction, the solution of Laplace's equation gave the equation of a straight line. The next coordinate was S. We solved for that also, and we found that here we did not get a straight line, we got a logarithmic behavior. Next, we took up the case of Laplace's equation in spherical polar coordinates. So we took up the first coordinate r, and we solved it. We found that the potential went as minus 1 upon r, kind of a behavior, but the electric field went as 1 upon r squared kind of behavior, and that is how it should be. If you take a static distribution of charges, then the electric field will always go off as 1 upon r, as you would have realized by your study of Gauss's law of electrostatics, particularly in the integral form. Next is the dependence on theta. This was the last topic that we took up. We found, this was the most difficult of the 9 cases that we have to consider while working with Laplace's equation. So this one, just a minute, please. Just a minute. Yes, sorry, just. This one gave v as a complicated function, log of tan, whatever. But, well, that's how it is. And then we solved for the electric field as well. That goes as 1 upon log of, 1 upon r sine theta. R can be any, can have any general arbitrary value. It is the dependence on theta that matters. So it goes as 1 by sine theta or cosec theta. Anyway, so that was the thing that we did. We shall now take up the last of the 3 coordinates in the spherical polar system, namely phi. We have worked with r, we have worked with theta, and now we shall work with phi. So let us go back to the general form of Laplace's equation in spherical polar coordinate systems. This is the general form of Laplace's equation. Del squared v is equal to, this is the r variation, this is the theta variation, and this is the phi variation. Now we shall take up a situation whereby, so far we have taken up v depending only on r and v depending only on theta. We have done these two cases. Now we shall take up the case of V depending only on phi. So if V depends only on phi and not on R and theta, then del V del R will be 0, del V del theta will also be 0. So this and this part will go away, and you'll just be left with this 1 upon R squared sine squared theta del to V del phi squared. So the Laplacian will be reduced to this specific form as per the nature of the problem you are now trying to solve. So that is what it is. Del squared V is 1 by R squared sine squared theta del d2V d phi squared is equal to 0. So since it's a one variable problem, we are no longer writing del 2V del phi squared, but d2V d phi squared. Okay, I've written something over here also. R and theta can be quite arbitrary, you don't know. So they can have any value. That doesn't matter really. Anyway, so this into this is equal to 0. This is the new topic that we are starting for the day. This into this is equal to 0. If that be so, 1 by R squared sine squared theta in general is not 0. It can only be 0. Well, sine squared theta can't be, 1 upon sine squared theta can't be giving you 0. Because sine squared theta will have to be infinity to give this thing 0, but sine doesn't accommodate any infinity. It goes only up to +1 and goes down to -1. So this can only happen, this can only be 0 when R will go to infinity. But that's not a general situation. So we'll just say that this thing is non-zero in the most general sense. V as a function of phi only, which means that d2V d phi squared is equal to 0. So when V depends only on phi, we will write d2V d phi squared is equal to 0. Fine then, again you are encountering the equation of a straight line. dV d phi is equal to a constant. That's the first integral. Remember the logical flow, the algorithmic flow in working with all these Laplace kind of problems. First you write the general equation, then you take the specific dependence given the you take the specific operator given the kind of dependence that you have. V depends only on phi in this case, therefore this operator. Thereafter you have to carry out two integrations. This is the first integral, dv d phi is equal to a, and then this is the second integral, v is equal to a phi plus b. So you have these two integrals, then we apply the boundary condition. What are the boundary conditions? Phi is equal to phi 1, v is equal to v1. So just let us see this diagram here. This is x, this is y, this is z. Phi starts from the x-axis. So this is phi 1, and here on this surface, v is equal to v1. We are looking at the spherical polar system. And here you go to another angle. This is like a swing door, except that the swing door is not rectangular in shape. It is like a half disc. And so this swing door goes to a new angle phi 2, where the potential is v2. Okay, so as soon as you are given these two boundary conditions, you put the boundary condition. So v is equal to v1, phi is equal to phi 1, a phi 1 plus b is equal to v1. Therefore, b is equal to v1 minus a phi 1. So put the value of b in this general equation. So v is equal to a phi minus a phi 1 plus v1. When v is equal to v2, phi is equal to phi 2, and all the other things remain. And so a is equal to v2 minus v1 by phi 2 minus phi 1, which is actually the slope of a straight line. You notice that you are to solve the equation of a straight line. So if you are solving the equation of a straight line, and if you're given two coordinates, x1, y1, x2, y2, what is the slope? Simple thing, y2 minus y1 by x2 minus x1. So that is exactly the thing that we have got over here, except that we are writing v2 minus v1 by phi 2 minus phi 1. So that is what it is. That's the slope of a straight line, and thereafter it's a fairly simple task. So v is equal to a phi minus phi 1 plus v1. Everything in terms of all the boundary conditions. This is your integral solution, but if you want to do a little bit of extra work, you write v2 minus v1 by phi 2 minus phi 1 into phi plus v1 minus phi 1 into v2 minus v1 by phi 2 minus phi 1. So this is the constant part. And so you work with these two terms, v1 minus phi 1 into v2 minus v1 by phi 2 minus phi 1, and this is what you end up with. So this part. So final answer is V is equal to V2 minus V1 by phi2 minus phi1 into phi. So this part, V2 minus V1 by phi2 minus phi1, is the slope of a straight line. This is in the form of Y is equal to mx plus c. And then this is the constant part. Okay, so that is the integral solution that you have got. Next is finding the electric field. Electric field is negative gradient of this potential function, which is minus 1 by r sine theta dv d phi phi cap. Okay, so if that is what you have, then all you have to do is to go back to dv d phi, which is equal to a, and a is the slope, this. All you have to do is to put all these things, minus 1 by r sine theta, a phi cap, minus 1 by r sine theta, a is v2 minus v1 by phi2 minus phi1 phi cap. So that is the electric field. So we have worked on the last of the coordinate dependence in this spherical polar coordinate system, the r theta phi system. And so let us just have a broad recollection of all the things we have talked about. We have talked about solving Laplace's equation in the three coordinate systems that we have got, namely Cartesian, cylindrical, and spherical. In each of these coordinate systems, there are three coordinates. So we have solved for Laplace's equation depending on any one coordinate within a coordinate system. So for three variables, for each of the three coordinates, there should be 9 different kinds of Laplace equations, 9 different kinds of mathematical problems we would work on. Out of these 9, the XYZ system, let me recall now, the XYZ system gives the solution of a straight line in all the cases. V is equal to AZ plus B. If you, instead of working with the Z variable, had worked with the X variable, you would have got V is equal to AX plus B. Or if you had worked with the Y variable, then you would have got V is equal to AY plus B. In all these three cases, you get the solution of Laplace's equation as the equation of a straight line. So Cartesian coordinate system is the Cartesian coordinate system is perhaps the easiest to work with when you're dealing only with one variable dependence. I stress on that thing again and again. Actually, solving for Laplace's equation as it depends on all three variables is a serious mathematical challenge. We are not getting into that. We are not here to do math. We are here to do physics at a level of fundamental conceptual clarity. So the three cases will give you 3 straight line solutions. What about the cylindrical system? Try to docket all these things clearly in your mind. In the cylindrical system, the Z solution will give you a straight line, fine. The phi solution will also give you the equation of a straight line, very good. But the S solution will not. So out of the 6 cases we have considered so far, X, Y, Z, S phi Z, S does not give the solution of a straight line. It goes as log of something, whatever that is. Log of S, A log of S. Okay, and then of course there's also an additive constant which we can absorb within the logarithmic function. Then in the polar coordinate system, we have got r, theta, and phi. R does not give the equation of a straight line. It gives a 1 upon r kind of dependence. See that? Minus a by r, not a into r, 1 upon r kind of dependence. Theta is algebraically the most complicated. It gives you a pretty complicated solution, log of tan theta by 2. So that's also not a very straightforward solution. So r and theta are not solutions of the equation of a straight line. But phi is. The phi coordinate gives you the solution of a straight line, the equation of a straight line. So if you gather all of these points together, you will realize x, y, z, all straight line solutions. S, phi, z, phi and z give you straight line solutions, not s. R, theta, phi, only phi gives you a straight line solution, not r and theta. So out of the 9 cases, 6 cases are fairly straightforward. They are just solving the equation of a straight line. So this equation of a straight line feature is a recurring phenomenon in Laplace's equation, because fundamentally, if you're solving a one-dimensional problem and somewhere in the operator there's this d2v d phi squared kind of a d2v d whatever variable squared kind of is equal to 0 kind of a structure, then a straight line is not to be unexpected. That is what it is. I intend to supply some extra notes on these concepts soon enough. But for the time being, we shall look at certain features of Laplace's equation, how to solve for Laplace's equation in a different context. So just remember, given Laplace's equation require 2 boundary conditions. Before we leave this page, I'll stress on that fact once again. Laplace's equation is solving a second order differential equation. What is the dependent variable in Laplace's equation? The potential function. So whenever you solve for the potential function, you have to work with the second order differential equation. And if you work with the second order differential equation, then you must have 2 boundary conditions. That is important. You have to have 2 boundary conditions. So potential, meaning you either have to solve Laplace's equation or Poisson's equation, whatever. Nevertheless, I mean, whatever you do, if it's a second order differential equation, both are second order differential equations, Poisson and Laplace. I hope you have not lost sight of the fact that del squared V is equal to minus rho by epsilon naught gives Poisson's equation. But if it is 0 on the right-hand side, then you have Laplace's equation. So the left-hand side is the same for both equations. And the left-hand side solves usually to the equation of a straight line. Whatever we hit, since it's a second-order differential equation, since the left-hand side containing a second derivative of the potential function, you cannot avoid working with 2 boundary conditions. So that is an important feature that we shall take up now in what we are about to begin discussing. So please just bear with me. Just give me a minute. Please confirm that you can see this thing. Hello? Can you please confirm?
Yes, sir.
Okay, thank you very much. Please mute the mic, all of you. Just give me a minute, please. Okay, I hope all of you can hear me. Certain additional properties we shall take up now. Boundary, in terms of boundary conditions. We have seen how to apply boundary conditions while solving for problems involving Laplace equation or Poisson equation. Laplace equation. We did not apply boundary conditions in the case of Poisson's equation. Let us see now. Here we have a situation where there's a volume. A volume always ends in a surface. I hope you are aware of that simple geometrical fact, and this is something that we have discussed quite a lot in the context of Gauss's law. So a volume contains a surface, bounded by a surface. The boundary of a volume is the surface. Boundary is the key thing over here. The solution of Laplace's equation. You follow this point carefully, very carefully. the solution of Laplace's equation, del squared V is equal to 0, which is uniquely determined within the volume if the value of V is specified on the boundary surface of the volume. Now, why are we talking about a boundary, I mean, volume? Because that's the most general case. So far, we have just talked about in all the examples we have worked upon, we have talked about only a one variable dependence. As soon as you talk about a one variable, X, Y, Z, let us say, dependence only on Z, you are confining yourself to only one coordinate axis. Or in the other cases as well, S phi Z or R theta phi. In all of these cases, you're confining your attention only to one coordinate axis. But in the most general sense, Laplace's equation can have dependence on the other variables also. So basically, as soon as you reduce your problem to have only one variable dependence, then you are confined along an axis. So you're solving a one-dimensional problem. But in general, it can have dependence on the other two variables as well. So it's a general three-dimensional problem. So the solution of Laplace's equation is uniquely determined within the volume. All three variables can be changing. If the V can depend on all three variables, if the value of V is specified on the boundary surface of the volume, value of V is specified at the boundary. For instance, in all of these problems, just a while ago we worked on the phi variable. V as depends on phi in the r theta phi coordinate system. What were the two boundaries we used? Phi 1, V1. Boundary condition is phi 1, V1 is V is equal to V1 at phi equal to phi 1. And similarly, V is equal to V2 at phi equal to phi 2. So those were the two boundary conditions. Now, if you are given a certain boundary condition, then depending on those two boundary conditions, Laplace's equation will have exactly one solution and nothing else. Let us try to understand. Suppose I give you a one variable problem. d2v dz squared is equal to 0. In the xyz system, let us say d2v dz squared is equal to 0. Then I will solve this equation. I'm just simplifying it for better understanding. V is equal to az plus b. Now you have got two unknown constants, a and b, which we have worked on already. And now I supply you two boundary conditions. And V is equal to V1 at Z is equal to Z1 and V is equal to V2 and Z is equal to Z2. Now using these two boundary conditions, you will get exactly one solution, nothing else. For instance, let us just see. Let us say that at Z is equal to 0, V is equal to 0. So if at Z is equal to 0, V is equal to 0, then immediately if you put these two conditions in the equation V is equal to AZ plus B, B will be equal to 0. Therefore, your solution will be V is equal to AZ. Okay. Then I say at Z equal to 1, V is equal to 1. Therefore, A will be equal to 1. So given these two boundary conditions, 0, 0 and 1, 1, Z equal to 0, V is equal to 0, Z is equal to 1, V is equal to 1. Given these two boundary conditions, you will have only one solution, namely V is equal to Z, just like Y is equal to X. Right? You will not get a solution like V is equal to Z by 2 or V is equal to Z squared. No. You just get only one solution. So the solution of Laplace's equation is uniquely determined within the volume if the value of V is specified on the boundary surface of the volume. Now, if you can extend this principle to a general third three-variable system, the same principle will hold. I mean, the proof is not very difficult, but I don't want to discuss the proof because for the time being, you're not going to be asked for the proof, but maybe I'll supply it later in a set of supplementary notes. The proof is not very difficult at all. All you have to do is that you'll say, let us say that V has got two solutions for the same boundary conditions. Let us say V has got two solutions for the same boundary condition, namely V1 and V2. So the two solutions will satisfy Laplace's equation del 2 V1 is equal to 0 and del 2 V2 is equal to 0. Take the difference of the two equations, so it will be del 2 V1 minus V2 is equal to 0. Now this will only work generally if V1 is equal to V2, meaning the two solutions must be the same. We can argue for that. Okay, so we have talked about a volume that does not contain charges. Now what about a volume? If the volume contains charges, then you are no longer looking at Laplace's equation, you're looking at Poisson's equation. Will the same principle hold? Well, yes. Why so? How so? If the volume contains charges, let us upgrade our discussion to a region where charges are contained. If the volume contains charges, same charge distribution, rho, then within it, V is uniquely determined if the charge density distribution within the volume is specified, along with the value of V on the boundary surface. So, of course, you'll have to be supplied the boundary conditions because we are working with a second order differential equation. And since it's a second order differential equation, it will be, you'll require two boundary conditions. Fine, that's there. But in addition, if the volume contains charges and the charge density is specified, charge density distribution function rho is specified, then again, the solution of V will be unique. You will not get two kinds of solutions for the same charge distribution and the same boundary conditions. Again, it's not a very difficult thing to do. All you have to do is start by saying that let us say that we can get two solutions, two separate solutions, V1 and V2 for the same set of boundary conditions and the same charge density. So then you will have del 2 V1 is equal to minus rho by epsilon naught and del 2 V2 is equal to minus rho by epsilon naught. Take the difference and you will have del 2 V1 minus V2 is equal to 0 because rho by epsilon naught is the same for both, they will cancel. And as soon as you've got del 2 V1 minus V2 is equal to 0, you'll go back to the previous situation by the same argument where, I mean, it's the same thing. Take the difference of the two Laplacian of the function, and you can argue that that can only happen when V1 is equal to V2. And so anyway, so this is a powerful argument. So what we do is that we will use this thing. As long as the solution of V satisfies Laplace's equation or Poisson's equation and meets the boundary condition, then it doesn't matter how you solve for V, because V in any case for those boundary conditions will be the same. And so we will avoid solving Laplace's equation and we will do this thing as we do in the method of images. We shall get to that soon enough. But before that, I will just touch upon the second uniqueness theorem. I mean, we have talked about the first uniqueness theorem, boundary conditions and uniqueness. Unique meaning only one of a kind. You will get only a unique solution, uniquely determined, unique. So that is the first uniqueness theorem. So the first uniqueness theorem had a charge-free region bounded by a surface. Its extension or corollary is there is there is some form of a charge density distribution bounded by the surface. Then there is also a second uniqueness theorem, not that we shall need it, but since we have talked about the first one, we shall also just state this thing. The proof of this thing is not so simple as I have verbally discussed in the first two cases. I'm just stating it. Here you have a situation where this is a volume. The volume contains charges. A continuous charge distribution of density rho, local density rho. So these dots are supposed to represent the charge density distribution. Now, charges are also made to sit on the surface, and this volume also has got pockets. So this is the surface boundary of a pocket. This is the surface boundary of a pocket. And charges are made to be in those pockets, and I hope you have not forgotten that charges will always gather on the surface. So this surface has got a charge Q1, this surface has got a charge Q2. So it's like um, some kind of a, cheese or something, where you have got air pockets inside, continuous distribution of matter, and then an air pocket. So these are like those pockets. And in the pockets, charges have been placed. So Q1 is residing on this surface, Q2 is residing on this surface. Outer boundary charges are also residing on the outer boundary surface. And inside, there is a continuous charge distribution, rho. So the electric field, we are no longer talking about potential, we are talking about the electric field E. The electric field is uniquely determined in the volume containing a specified charge density rho if the total charge on each conductor is known. And the outer boundary can be a conducting surface. So we have just upgraded the discussion to something more. First, we talked about no charge anywhere, just an empty volume with a bounding surface. Second is, we have got situation whereby this space is filled with charges of uniform density. The third case is we have a situation whereby, in addition to this smooth distribution of charges, you have isolated charges of value Q1, Q2 placed on the surface. It's like the difference that you have, if you apply jam or let's say butter on bread, the butter will be like smooth distribution, homogeneous or rather continuous distribution of charges. That will be the butter. And on the butter, you drop grains of sugar. Sugar comes in little grains. So sugar does not have a continuous distribution. So these charges Q1, Q2, or anything on the outer boundary are like those grains of sugar. They are isolated point-like charges. So there are two kinds of charges involved over here. One are the isolated point-like charges, and the other is the butter-like continuous distribution of charges. That has got a charge density function rho, and these things have got individual charge values Q1, Q2, etc. So when you have this third injection of charges, isolated grains of charge, point charge, then how does the electric field get affected? The electric field is uniquely determined in a volume containing a specified charge density rho if the total charge on each conductor is known. So the outer boundary can be the conducting surface. This is the second uniqueness theorem. Be mindful, we are no longer talking in this case about the potential function, but the electric field. Anyway, I shall not labor this point too much. I'd rather be concentrating on these first two things, the uniqueness theorem and its corollary, its extension, something that can be derived from it. Let us see how. We'll discuss a simple case of the method of images. Let's try to see what is it now. First, let us look at it geometrically. I have made an error here. There should be Z. This is X, this is Y, and this is Z. Okay, this is Z. On the XY plane, there is a grounded conducting conductor, a plain conductor, a sheet of copper, let us say. Copper is a good conducting material. It's a sheet of copper, and it is grounded on the XY plane. Grounded means that its potential is zero. I hope you are aware of that fact. And the sheet is going to infinity in both directions, both along the x direction and the y direction. So the sheet is going to infinity. So it's an infinitely extended conducting surface as in a sheet of copper. And that sheet of copper coincides with the xy plane where z is equal to 0. Okay. Now you are doing something. At this height d above the xy plane, at the height d, where the coordinate is 0, 0d along the z-axis. I made a mistake over here. Please just note the correction. This is z. This should be z. So at this height d, this coordinate will be z on the z-axis. at this point will have the coordinates 0, 0, D. Okay. At this point, you bring in a positive charge Q, small q. So the question is, as soon as you bring in this Q over here, after that, what is the potential in this region above the plane? Normally, you would have thought that, I mean, what is the big deal? You have a charge Q over here, the potential is very easily known. What is the potential? Q divided by 4 pi epsilon naught into the distance from the position of the charge. That is what it is. Q by 4 pi epsilon naught r, let us say. You place the charge at the origin of coordinates. And so the potential at a distance r will be Q by 4 pi epsilon naught r. But is that so? Answer is no. It's not as simple as that. Here's the question I have written. Q induces charge. Here's the statement I've written. Q induces charges on the conducting plane. This Q is positive, induced charges are negative. What is V above the plane? Let us try to understand this thing. As soon as you bring in this positive charge, it will be exerting its electric field in all directions. Follow carefully. Under the influence of this electric field, this sheet, it's a conducting sheet. So if it's a conducting sheet, then it contains charges that move freely. It's not a wooden sheet, wooden platter or plate or anything. Had it been an infinitely extended sheet of wood or plastic, then there would have been no problems for you, because wood, plastic, these are insulating material. So there is no free movement of charges in such a material. So your Q would have come over here, nothing would have happened to this plane, and you could have very simply you could very simply apply your potential formula, as you know from Coulomb, due to a point charge. But that is not what happens. Since this is a conducting sheet, what will happen is that as soon as you have a plus Q charge over here, all the positive charges in this sheet will tend to move away. This is a positive charge. Its effect will be to repel the positive charges from the sheet below, on the sheet below. So the positive charges will tend to move away to as great a distance as possible. And meanwhile, the negative charges will get attracted towards the plus Q, and so the negative charges will come closer. So basically here you will have a pocket whereby there will be more negative charges than positive charges. The positive charges will be repelled to great distances away on the plane, whereas the negative charges will be drawn towards this point at the center of the plane. So the local charge homogeneity will be lost. If this Q were not to have been there, all the charges would have uniformly blended with one another, and you would have had a homogeneous distribution of charges and no electric field above, because all the positives and the negatives would have cancelled one another out. But here, that is not what will happen. So now with this pocket of negative charges, that will create an attractive electric field. This will create that will create an inwardly directed electric field, and whereas this charge will be creating an outwardly directed electric field, and so there will be now two sources of electric field. This point charge above with a positive value, and these negative charges gathered under it with charges gathered under it with a negative value. And the total potential will be due to both these kind of charges, this isolated point charge above and these charges which are gathered over here. So under the influence of that, the question is, what is V above the plane for Z greater than 0? I'm sorry, once again, this is Z. In my hurry, I wrote this thing as X. X is this direction, Y is this direction, Z is above. So be mindful of that. So basically what we shall have to do, we shall have to solve Poisson's equation for Z greater than 0. Why Poisson's equation? Because above the plane there is one point-like charge. So this whole region contains one charge. And so this is not a charge-free region. So if you want to solve for anything... Hello? What is going on? Somebody please mute the mic. What happened? Yes, please. Thank you. Please mute the mic. Just a minute. Okay, thank you. Okay, so in this region above the plane, there is one point-like charge at least. So this is not a charge-free region. So if you have to solve for the potential function, you must solve for Poisson's equation, not Laplace's equation. Remember, Poisson's equation is del squared V is equal to minus rho by epsilon naught, whereas this thing, Laplace's equation is del squared V is equal to 0. Now, what are the boundary conditions with which? Here we have the idea of uniqueness. Solve Poisson's equation for z equal to z greater than 0 when v is equal to 0 at z equal to 0. On this plane, v is equal to 0. That is the first boundary condition. See, if you have to solve Poisson's equation, which is a second order differential equation, you must require two boundary conditions along the z direction. That is, you're solving for Poisson's equation along the z direction. So on this plane, you have the conductor on the xy plane, the conductor which is placed there is grounded. Grounded meaning zero potential. So V is equal to 0 at Z is equal to 0. It is grounded. Now the other thing, V goes to 0 when you go to a great distance away from above the plane. You go to a great distance above the plane when R is greater than, much greater than D. R squared, what is R? R squared is equal to x squared plus y squared plus z squared. Why so? Because the farther you're away from, you have got a point charge over here and you've got induced charges over here. D is not at a great height above the plane. Now you know very well that if you go to infinity, potential is 0. That is the way we do it. But we are not going to infinity. We are going to a great distance away from both this plane and the location of the isolated charge Q above the plane. That is what we are doing. So the farther we go, more and more will the potential tend towards 0. So these are the two boundary conditions. V is equal to 0 at this plane and V is equal to 0 at a great distance above the plane, much greater. So those are the two boundary conditions. Within these two boundary conditions, within these two boundaries, we shall have to solve Poisson's equation. What is uniqueness theorem saying? Uniqueness theorem is saying, uniqueness theorem or its corollary, it is saying that V will be uniquely determined. Given two boundary conditions, only one V could be found and nothing else. Can we then, today a lot of distraction is happening. I don't know why. Please mute the mic. It's a very simple instruction to make. Okay, so these are the two boundary conditions within which you shall have to operate. Now, what did I write earlier? As long as the solution of V satisfies Laplace's equation or Poisson's equation, whatever, as long as the solution of V satisfies Laplace's equation and meets the boundary condition, then any method for solving V is correct. You try to follow this logic now. We have got a rather difficult mathematical problem to work on. What is the mathematical problem? That here we have got a plane full of charges. The positive charges have been driven away to infinity. The negative charges have been brought closer. We do not know how the charges are distributed. Just the presence of a point-like charge above this plane has created this disruption on the plane. So things have moved away, plus charges have gone away, minus charges have come closer. So if that is the situation, then one problem is that we do not know what is the charge density, surface charge density distribution function. How will we solve for the potential if we do not know that? Well, we don't really have to know that. We are just going to use the uniqueness properties of Laplace's equation. Let us see how. Imagine that you no longer have the plane. The plane has gone away. Instead of having the plane at z equal to 0, follow this point with great attentiveness, please. Instead of having this conducting plane at z equal to 0, you say that I have got a minus q charge placed at the same distance d but below the plane. Here I have written the z correctly. This is the z axis, this is the x axis, this is the y axis. Earlier we were solving for a problem in which we had this plus q charge and we had a plane full of charges coinciding with the xy plane, an infinite plane full of charges coinciding with the xy plane. But now we have taken that plane away, and instead of that plane, we have put a minus q charge just below the plane at the same distance d as it is above, except that this coordinate will be minus d. This is the method of images. You have a plus q charge over here. Its image is minus q here. Let us now see. You are required to find the potential at any distance, any coordinate position x, y, z above the z equal to 0 plane, right? That is the question. So what are the contributions to the potential at any arbitrary point above the z equal to 0 plane? At any arbitrary point, what is the contribution to the potential? Well, the first contribution comes from the charge plus q, from which the position of our study is given by the coordinate r1, vector r1, or radial displacement r1. What is the value of the radial displacement? Let us see. Remember, the reference point is the plus q charge. What will be the coordinates here? Let us see now. X, y, as it should be, and z. With respect to the origin, this height is z. But with respect to this charge plus q, this height is z minus d. I hope you are following the simple geometry. With respect to the origin, this height is z. This height is z with respect to the xy plane, where z is equal to 0, this height is z. But with respect to this line or this position where the plus charge q is kept, the z coordinate height is z minus d. So this radial vector will have the scalar length of square root of x squared plus y squared plus z minus d squared. Okay. Right now, the plane is no longer there for you. Instead of the plane on the instead of the conducting sheet on the xy plane, you have taken that plane away and you are saying that its equivalent role is to be played by a minus q charge just below the origin. This is the subtle point. This point charge minus q, this point charge minus q is throwing a radial line to our position xyz, which has got a radial length of, straight line length of r2. That is the length that you have. What is its coordinate value? With respect to r2, what is the coordinate value of xyz? Let us see. X and y remain the same. With respect to the z equal to 0 plane, this height would be z. But now you have gone below the plane by a distance of minus d. So basically this height with respect to this thing will be z minus of minus d. Z minus of minus d. Here it was plus d, so it was z minus of plus d, but here it is minus d, so this height will be z minus of minus d, which is z plus d. So with respect to this minus q charge, this point will have the scalar length of r2, which is equal to square root of x squared plus y squared plus z plus d whole squared. You must be wondering, why am I suddenly going off on a wild goose chase of solving for plus Q and minus Q. Our real problem was plus Q up there and a conducting sheet. I mean, I've suddenly taken the conducting sheet away and I've placed a minus Q charge below the plane where the conducting sheet should have been. Conducting sheet should have been, instead of taking up a minus Q. I mean, you might be wondering, why am I doing that? Here's the answer. We are solving not the problem that we have been given, rather we are solving an equivalent problem. And what is the equivalence? Let us now see. What is the potential here? Potential will be due to this plus charge. It will be 1 by 4 pi epsilon naught Q by R1. And due to this minus charge, it will be minus Q 1 by 4 pi epsilon naught minus Q by R2. Okay. Now, at Z equal to 0, at Z is equal to 0, what is the boundary condition we have been supplied? V is equal to 0. Let us see, do we get, by this equivalent potential function, do we get that boundary condition at Z equal to 0? At Z is equal to 0, R1 is equal to R2. Why? Because at Z is equal to 0, you just see this thing. When you have Z is equal to 0, it will be x squared plus y squared minus d whole squared. Minus d whole squared will just be d squared again. So it will be x squared plus y squared plus d squared. R1 will be x squared plus y squared plus d squared. At Z equal to 0, R2, this thing, as written here, R1 written here. R2 will be equal to x squared plus y squared plus d squared. Z is equal to 0 here, Z is equal to 0 here, gone. So you will have R1 will be equal to R2. If R1 is equal to R2, 1 by 4 pi epsilon naught Q by R1 minus Q by R2 will be equal to 0. So V is equal to 0. So we have satisfied the first boundary condition by the potential function that we have equivalently crafted. This is the potential function that we have got. And with the help of this potential function, we satisfy the first boundary condition. Now, what about the second boundary condition? The second boundary condition says that when R becomes very much greater than D, R becomes very much greater than D, meaning D becomes so small with respect to all the three coordinates, X, Y, and Z. Let us try to see. X meaning you're going this way, Y, you're going this way, Z, you're going this way. You've gone to a great, great distance. You don't even have to worry about X and Y. Let us just worry about, you've gone to a great, great height above the Z equal to 0 plane. As you're going to a very great, great height, Z is increasing. So Z increasing with respect to D, you can, ZD becomes very small. Similarly, Z increasing with respect to plus D, again, it's D becomes very small comparably. So when you have these two values of Z becoming very, very much greater than D, then progressively these two things, R1 and R2, will become equal to each other progressively. D will become so small that eventually, I mean, let us say Z has become infinity. Hypothetically speaking, ideally speaking, infinity minus D and infinity plus D will make no difference to infinity. Infinity is infinity. Of course, one mustn't say we are doing infinity minus infinity, but I'm just giving you a simple hypothetical point. When we are dealing with infinity, we have to be careful. So when Z becomes very much greater than D, then R1 and R2 will become nearly equal to each other. So when progressively they become nearly equal to each other, V will tend to go to 0. And at infinity, of course, V will become 0. So the two boundary conditions of our original problem are satisfied by this potential function. This potential function we have got not from this case of an isolated plus charge Q and this conducting sheet. We have not got it from there. Instead, what we have done is solve an equivalent problem. And what is the equivalent problem? Plus Q remains what it is, but the sheet is taken away, and instead of the sheet, we have taken a minus Q charge down here. So with that minus Q charge down there, we have got a simple potential function. But what we find is that this potential function meets our two prescribed boundary conditions for the original problem that was presented to us. If that is so, then the two boundary conditions are met for plus q and also minus q, hence Vxyz, this one, for plus q and minus q, also stands, very important, I've stressed it with double underlining, also stands for the plus q and the conducting plane problem. This was the original problem by the uniqueness theorem. What is the uniqueness theorem telling you? Let us get back to that. Let us get back to the potential business, not the second uniqueness theorem. As long as the solution of V satisfies Laplace's equation or Poisson's equation. In this case, we are to solve Poisson's equation. As long as the solution of V satisfies Laplace's equation or Poisson's equation and meets the boundary conditions, indeed it does, then any method for solving V is correct, as in the method of images. I mean, ideally, you would have, finding the potential, you would have worked out the Poisson equation to solve for this thing. But you could only work it out if you knew how this charge was distributed on the plane. You have no a priori way of knowing that. But you know the uniqueness theorem is giving you a powerful equivalent way out, an escape route. And what is that escape route? That if this boundary condition, which is appropriate for this problem, is also simulated by another problem of an equivalent nature, then the solution that you get from the simpler equivalent problem will also be the solution of this problem. Because uniqueness theorem says that there can be no other solution for the same boundary conditions. So that is what it is. We just have to, so basically, instead of solving this problem with the help of these boundary conditions, we have got an equivalent potential function by solving a different problem and just establish that that equivalent potential satisfies the two boundary conditions we have been given. And that way, we have got the solution for the potential by the method of images. Why images? You have a plus q charge here, you have a minus q charge here. Image, you stand in front of a mirror. Your image will be behind the mirror by the same distance as you are in front of the mirror. If you walk towards the mirror, your image will walk towards you. If you walk backwards, back out from the mirror, your image will also back out from you. So here you have a plus q charge. So let's say this xy plane is the mirror plane. You have a plus q charge over here. Whatever be its distance from the plane, d, on the other side, you have a minus q charge, same magnitude, but minus q, meaning just as it happens in the mirror image, your right hand in real life becomes the left hand in the mirror view. So that is what it is. And your left hand becomes the right hand in the mirror view, in the mirror image. So that is what happens. And so that's something like plus goes to minus. But the distance is still the same, except that it's below, so it's got a minus sign. So this is the mirror solving Laplace's equation by the by the image method. Now, we still have to do something extra. If we had known the surface charge distribution, then we could have solved this problem by Poisson's equation instead of by the method of images. But we have done a back to front kind of a scenario. We have solved a different kind of a problem and found the potential function and said that the potential function satisfies our original problem due to the uniqueness theorem. Very good. But what about the surface charge that is induced? Can we see what the surface charge is going to be like? Surface charge density function. Let us see. We have discussed this point earlier also. We are extending the problem. So this point is that, this discussion is that the electric field above a plane conductor is E is equal to sigma by epsilon naught z cap. Okay. But the electric field is also negative gradient of a potential function minus dV dz. Therefore, minus dV dz is equal to sigma by epsilon naught. We were, this E is, in case you are having any difficulty recalling what I'm talking about, E is equal to sigma by epsilon naught z cap. This is the thing that we discussed while solving for Gauss's equation, Gauss and conductors. Solving for Gauss's law of electrostatics above a plane, and then applying the idea for a conductor. So you have a plane conductor, above a plane conductor that contains charges where surface charge density is sigma. Sigma by epsilon naught is the electric field. It remains constant regardless of how great a distance you are or how close you are to the conductor. This point I discussed in the class earlier. I'll supply you the notes and the lecture recordings very soon. It's after the exams, they are overdue. I'm sorry about that, but please just bear with me. Anyway, so minus dV dz is equal to sigma by epsilon naught. Okay. dV dz, we are only worried about the variation of the field along the z direction here. So, but V depends on X and Y also, but we are moving up and down along the Z direction. So X and Y are not being changed. So just to impress that fact, we are taking the partial derivative of V with respect to Z. So dV dz is equivalently to be seen as del V del Z. And what is V? V is this function, 1 by 4 pi epsilon naught Q into 1 by R1 minus 1 by R2. So that is what it is, Q 4 pi epsilon naught. And then we shall have to take the Z derivative of R1 and R2 because both of them contain Z. Okay. So let us see now. Q by 4 pi epsilon naught stays outside. We are now going to take the derivative of this thing. Minus R1 is equal to x squared plus y squared plus z minus d whole squared raised to half. Okay, and R2 is x squared plus y squared plus z plus d whole squared raised to half once again. So we shall have to take the derivative of that thing. What we shall do is minus over there, then half x squared plus y squared z minus d whole squared raised to minus 3 half. Then you go inside, but chain rule basically. That is what the only thing we are doing. 2 into z minus d. Okay. And then what about this part? This minus is this, minus 1 into, same thing, minus half into x squared plus y squared plus z. I'm sorry, I made another mistake over here. It should be z plus d, z plus d, z plus d whole squared, z plus d whole squared raised to minus 3 by half. Please just make that correction. 2 errors over here. First error is this one. It should be z over here, and here it should be z plus d whole squared raised to minus 3 half into, then taking the derivative, 2z plus d. Okay, let's now see what we get. The 2 and the 2 cancel, this 2 and this 2 cancel. You have a minus over here, and you have a minus and minus, which is plus over here. Okay, when z is equal to 0, you will get, follow carefully. When z is equal to 0, you will get x squared plus y squared plus d. Z will be 0, so minus d squared will be equal to plus d squared. Okay, this will be 0. So minus here and minus d over here will give you a plus d overall. Similarly, minus and minus will be plus. Here, again, z is equal to 0, x squared plus y squared, z plus d will just be plus d squared. So x squared plus y squared plus d squared raised to 3 half. Z is 0 here, it will be another d. Now, sigma is equal to minus epsilon naught dV dz. We are getting it from here. Sigma is equal to minus epsilon naught dV dz. When z is equal to 0, dV dz will be equal to q by 4 pi epsilon naught. In the denominator, you will have x squared plus y squared plus d squared raised to 3 halves. And there you will have minus into minus plus d here, and here you will have minus into minus 1, again a d here. So d plus d will be 2d. So that is what it is. So sigma x, y, z equal to 0 on the xy plane on the xy plane, your coordinates will be sigma xy 0 will be equal to minus epsilon naught into q by 4 pi epsilon naught into 2d by x squared plus y squared plus d squared raised to 3 halves. Okay, so this 2 and this 4 will cancel to give you a 2 pi. Epsilon naught and epsilon naught will cancel, and sigma xy0 is equal to minus qd by 2 pi x squared plus y squared d squared raised to 3 halves. So surface charge density at z equal to 0. So basically, what is it? Now we have, going back to front, we have been able to calculate what the surface charge density is going to be like. This is the surface charge density, which if we had known the surface charge density, then we need not have worked on the equivalent problem. We would straight away have got the potential function. But here, by using the method of images, we have got the potential function V. Then, with the help of that potential function V, we go back to front and find the surface charge density. What about the total charge induced on the xy plane? Very simple thing. Take the surface charge density anywhere on the xy plane. You can see for yourself that as x and y go to infinity, this will become infinitely large. Surface charge density will become 0. As at infinite distance, surface charge density will be 0. At this point, at the origin where x and y are 0, the surface charge density function when x and y are 0 will be minus qd by 2 pi d cubed. Therefore, minus qd q by 2 pi d squared. That will be the surface charge there. So it will be highest just vertically below the plane, below the point charge q plus q. Okay, so we'll just work on this last part. The total charge induced on the xy plane is Q is the total charge, surface charge density times the surface area element, and then taking the full surface integral. It will be convenient to apply cylindrical coordinates. X squared plus y squared is equal to s squared. So surface charge density will be equal to minus qd 2 pi s squared plus d squared. X squared plus y squared is equal to s squared, cylindrical coordinates. So that is what we are doing. And what about dA? dA will be on the plane, on the z equal to 0 plane, the disk of a cylinder. S d phi dz, ds, 1 cross 2. I hope you have not lost sight of that fact as well. 1 cross 2. In the, take the cylindrical coordinate system line element, dl is equal to ds s cap plus s d phi phi cap plus dz z cap. 1 cross 2 will give you this thing, s d phi s cap, z cap, s d phi ds z cap, but we are only taking the magnitude of it. So all we have to do is that what is the total charge induced? What is your instinctive answer? We shall see. You don't even have to work this thing out to know what the final answer, if you have a good physical insight into the problem. Sigma is equal to minus qd divided by 2 pi. Those are constant quantities coming out. Then you will have 1 by s squared plus d squared raised to 3 halves. Okay, then s ds d phi, s ds and d phi. This is a 2 integral over 2 variables, surface integral. So we have broken that surface integral into 2 line integrals. One is over phi, which has the limits of 0 to 2 pi, and the other is over s ds. So what are we doing basically? If you look at this plane, starting from the origin, we are going far out as much as we can along the s direction. S squared is equal to x squared plus y squared, that s, as in the cylindrical system, s. And we are also going around along the phi direction. Basically, we are gathering all the charges that have been induced in the plane. Okay, so that is the logic we have to apply over here. So, okay, so d phi integrated will give you 2 pi. So this 2 pi and this 2 pi will cancel, and you'll have minus qd. Next is you will have, going from 0 to infinity, s ds, I'm writing as, just see, some algebraic manipulation is going on over here. S ds, I'm writing as half ds squared. When you take d of s squared, what will you get? You will get 2s ds. That 2 and this 2 will cancel, but instead of that, s ds I'm writing as half ds squared. Okay, u is equal to s squared plus d squared. That is how we are writing it. And du is equal to ds squared. Basically, we will just have, this will be u raised to 3 halves. So u raised to 3 minus 2. This will be du. You have minus qd by 2 outside. Then when we integrate this thing, we will have e raised to minus 3 halves. Integrated will give you u raised to minus half. U is s squared plus d squared. And then in the denominator, you'll have a minus half as well. This half and this half will cancel. This minus and this minus will cancel. And you'll just have qd. And here it will be 1 by s squared plus d squared going from 0 to infinity. When you put the upper limit infinity, infinity squared, infinity of course. So putting the upper limit, it will be 1 upon infinity, which will be 0. And putting the lower limit, it will be s equal to 0 will give you minus 1 upon square root of d squared. And the square root of d squared will give you d. That d and this d will cancel, and you'll have minus q. So the induced charge plus q is equal to minus q on the z equal to 0 plane, and that is exactly what you should have. Q is the total charge, capital Q is the total charge that is induced on the plane, and that total charge will be equal to minus q. Why so? Here I've put plus q charge. So the induced charge on this plane will be nothing less, nothing more. If it is anything more, then where's the extra charge coming from? You have to believe in the principle of charge conservation. And if it is less than minus q, I mean, in magnitude, that is, less than minus q, I mean, if it induces less amount of charge, then there will be an imbalance. I mean, there will be a force imbalance. So as soon as you bring in plus q charge over here, all the positive charges will be driven to infinity, and the negative charges brought forward, gathered in total, will be equal to minus q. That minus q and this plus q will make this whole system charge plus the field have some sort of a charge balance kind of a situation. So the induced charge will be equal to minus charges induced on this conducting plane will be equal to minus q. Okay, last bit to work on, and we have a few minutes. We should be able to finish this thing. What about force? We are no longer looking at plane and point charge. We are again going back to plus q and minus q. Plus q up there, minus q down there. What is the force between these two charges? Force is minus 1 by 4 pi epsilon naught q squared by 2d squared. That is the distance, Coulomb attraction between the two charges, the charge and its image, z cap. Work done. Always remember, work done is against this attraction or repulsion or whatever that you have. So it will be minus f dot dl. So work done will be minus and minus will be plus q squared by 4 pi epsilon naught 4z squared. dl is dz z cap. That is what we write over here. Infinity to z. Infinity to z, you have brought it. And so when you integrate this thing, w will be equal to q squared by 4 pi epsilon naught. 1 by 4 stays outside. Z raised to minus 2 integrated will be z minus 1 by minus 1, infinity to z. So minus q squared by 4 pi epsilon naught. So this minus will come here, it will be 1 by 4z. Infinity to d, those are the limits. Lower limit, 0, upper limit, plus d. So 1 by 4d minus q squared, 4 pi epsilon naught, 4d. This is the energy of the system, meaning this is a bound state, negative energy. So to do work in bringing the charge from infinity to here, you supply that work will go into the energy of the system, and that is its value, minus q squared by 4 pi epsilon naught 4d. Anyway, so we have discussed the method of images in detail with the help of a simple example. I'm sorry about 2 errors. There is 1 error here. I'll correct these errors and supply you these notes. I'll also add a few supplementary points to this discussion, particularly about all this boson, this uniqueness business, all that. So after your exams, I haven't updated your study material, so that will have be done soon. By Deepavali, I think everything will be updated completely. Deepavali vacation will be the week after the next. So before that, we have 3 classes. We have a class on Friday, and next week also 2 classes. And today we have a tutorial. We shall be given a new tutorial sheet to work on. So with that, I stop the day's discussion. If you have anything to ask me, you may ask me. Otherwise, we can all log out. I'm stopping the recording as well.
Sir,
Yes, sir.
sir, this method of images, is it applicable only for straight